We're going to take a look at sequences and series now. Beginning with sequences. A sequence used to be called a progression. It's a collection of numbers or objects ordered. So there's a first, a second, a third, and so forth, an nth one for each natural number. Sometimes, in fact, a zeroth one is considered. All right. A sequence then is actually a function from the natural numbers to a set. In our case, usually the set will be the real numbers. And one writes a sub n, instead of a of n. So there's a first, the second, the third, the fourth, the fifth, and nth term to the sequence. Right? We're going to be interested in when these situations where these sequences approach a particular value. And they're very useful in approximating particular numerical values. So a sequence an is said to approach a, and one writes the limit of an as n approaches infinity here is equal to a, or an approaches a as n approaches infinity if, now this is the definition here, so this is going to happen if for each number epsilon, no matter how small, greater than 0, there is a capital number n, so that the difference between an and a in absolute value is less than epsilon whenever you take n larger than n. For all these n larger than n, an differs from a by less than epsilon. Some examples. The limit as n approaches infinity of the sequence 1 over n is equal to 0. 1 over n approaches 0. The limit as n approaches infinity of 1 over 2 to the n. So this is a half, a quarter, an eighth, a 16th, a 32nd, and so forth. This is also equal to 0. The limit, for example, as n approaches infinity of, let's say, 3n squared plus n plus 1 over 2n squared plus n minus 1, this is going to be 3 halves. As n gets very large, the leading coefficients here, the 3 and the 2, dominate the picture, and this gets close to 3 halves. And in fact, for that matter, the following holds. If an is f of n, and the limit as n approaches infinity of f of n is equal to a, this is the limit as, the limit as x approaches infinity of f of x is a, right? Where an is f of n, then the limit as n approaches infinity of an is also equal to a. So here, for example, if this was f of x, 3x squared plus x plus 1 over 2x squared plus x minus 1, then the limit as x approaches infinity would be 3 halves. So consequently, the an's have to approach 3 halves also. All right. The limit of an is said to be equal to infinity if for each number n, there is a number m, so that an is larger than n when n is larger than m. Right? It's said to be minus infinity. I'll write it out here. Limit of an is minus infinity if for each number n, however large and negative, there is an m so that an is less than capital N when you take the terms n which are beyond the mth one. Right. Several rules here hold, only a few though actually. Right. If an has its limit a, and the limit of bn is b, and f is continuous, then, first of all, the limit of an plus bn is equal to a plus b. Likewise, the limit of an minus bn is a minus b. The limit of an times bn is equal to a times b. Right? And the limit of an divided by bn is a divided by b, providing b is not 0. Okay, so the limit of sum is sum of limits, limit of products, product limits, limit of quotients, the quotient limits, just as for ordinary limits. And the proofs for this are essentially the same. If an gets close to a and bn gets close to b, then an plus bn get close to a plus b. Right. Also here now, the limit of f of an is f of a, if f is continuous. And a couple of simple things happen here. One of them is that the limit of a constant times an is a constant times a. And finally here, the limit of a sequence which is constant, c, 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 or if this was 2, the sequence that consists of 2 and then 2 and then 2 and then 2 and then 2, is that constant. So, here are some rules involving limits. The definition of the limits for finite limits and the definitions of the limits for infinite limits. Another property of limits, which frequently allows you to evaluate limits, is as follows. There's a couple of such properties. If you've got an, bn, and cn, with an approaching L, and bn approaching L, and cn is between the two. So if an is less than or equal to cn, is less than or equal to bn, then cn must approach L. It's sometimes called squeeze theorem. Cn is squeezed between an and bn. And when an gets within epsilon of L and bn gets within epsilon of L, Cn will have to be at epsilon of L also. So that'll tell you how to find how far down the sequence Cn you have to go in order to be epsilon close to L. Second property is the following. If an is increasing which means that an plus 1 is greater than or equals to an for each n. Right? It'll be said to be decreasing if an plus 1 is less than or equal to an for each n. So an is increasing, and bounded above, then an has a limit. Right? In fact, it has a finite limit, and any sequence which has a finite limit is said to converge. If it has an infinite limit, it's said to diverge to that limit. So it can be said to diverge to plus infinity or to diverge to minus infinity. If it doesn't have a limit at all, it's also said to diverge. So if it doesn't converge, the sequence doesn't converge, then it's said to diverge. Diverge means does not converge to a finite limit. In fact, the limit is the least upper bound. An approaches L equal to the least upper bound of the an, or the supremum of the an. This is not difficult to show either. And sometimes you can use this fact that if the sequence is increasing, let's say, and bounded above, or conversely if it's decreasing and bounded below, where bounded above here means that there's some number that all the terms are less than, then it has to converge. And sometimes you can use that fact, and here's an example. Suppose we take a look at the sequence that looks like this. 1, or if you want, think of it as the square root of 1. The second term is going to be the square root of 1 plus the square root of 1. The third term is square root 1 plus square root 1 plus square root 1, and so forth. This is a sequence an. Right? To show that this converges, or has a finite limit, we'd like to see, for example, that the function, since it's increasing clearly, we simply need to see that the sequence is bounded above. So let's show that an is always less than, let's say 10. This will make it bounded above. Well, the first term is less than 10. Right? And if the kth term is less than 10, then the k plus first term is equals to 1 plus the kth term, then square root. This is how you get the k plus first term from the kth term. All right? So this is less than the square root of 11, because this is supposedly less than 10, which is less than 10. So 10 is actually a very bad bound, but it shows that the sequence is bounded above, and since it's increasing, it must have a limit. Now we can actually get at that limit, because we have ak plus 1 squared is equals to 1 plus ak from this. So this sequence right here is the same as the sequence right here, and this approaches the limit, which is going to be a squared, and this consequently must approach 1 plus a. So we must have that a squared is equal to 1 plus a, or a squared minus a minus 1 is equal to 0, where a is the limit. Let's just say a is equal to 1 plus or minus the square root. B squared here is 1 plus 4 over 2. Right? Well, 1 minus the square root of 5 over 2, 1 minus the square root of 5 over 2 is negative, so that can't be the limit. The limit has to be 1 plus the square root of 5 over 2. So here, knowing that the sequence was increasing and bounded above, we knew that it had a limit. Knowing that it had a limit, we could then write this equation here, which would allow us to determine the limit. Right? So sometimes, knowing that the sequence converges allows you to find a limit. If the sequence didn't converge, see, if this was infinity, infinity squared equals 1 plus infinity could hold if the sequence approached infinity. Right? But not the case if we know that it has a limit. Okay, so the squeeze theorem, sequence is squeezed between two that converge to the same number, then it has to converge there too. And increasing sequences which are bounded above must have a limit. Well, we next want to take a look at series. Now, series are formally things that look like this. A0 plus A1 plus A2 plus, and so forth, plus AN plus and so forth here. Now, this is just formal because you can't really add up infinitely many terms. However, you get the sense that you can. For example, if you consider something like 1 plus a half plus a quarter plus an eighth plus and so forth here. 1 and a half, then you have 1 and 3/4, you have 1 and 7/8, 1 and 15/16, and it's clear that there's a sense in which this should be said to be equal to 2. It's going to get as close to 2 as you like, and never go beyond 2. We write summation n equals 1 to infinity of AI, for example, to indicate this, or summation n equals 0 to infinity of AI if the particular series begins with a 0, so that if there's a zeroth term here. And we'll talk about this being equal to a number s sometimes. And here's how s is defined. The summation n equals, let's say, 1 to capital N of AI is, by that is meant A1 plus A2 plus until you get up to A sub capital N. This is called a partial sum. And if this is equal to Sn, right? So if this happens, this is equal to Sn, and Sn is a sequence now. If it approaches S, then we say that summation AI, I'm going from 1 to infinity here, or AN, same thing, AN, N goes from 1 to infinity, is equal to S. If the partial sums have a limit of S, then S is said to be the sum of the series. So S here is called the sum of the series. Now, there's a particular type of series here that's easy to sum on certain circumstances. And it's the series that begins with A, and then you add A times R, plus A times R squared, plus AR cubed, plus and so forth. Let's consider the partial sum so that this goes up through AR to the capital N, let's say, and let's denote this by Sn. It's the sum from 0 through n of AR to the 0, AR to the 1, AR to the I. Now, note what happens here if we multiply this by R. RSN is equals to AR plus AR squared plus AR cubed plus and so forth. We end up with AR to the N plus AR to the capital N plus 1. Now if we take the difference here between this and this, we end up with Sn minus R times Sn, which we can factor the Sn out of and get 1 minus R times Sn is equals to, now here we've got A. All these terms when we subtract are going to be 0, and we're going to have A minus AR to the N plus 1. So we can tell what Sn here is here then. This is equals to A minus AR to the N plus 1 over 1 minus R. And now, if absolute R is less than 1, then R to the N will approach 0. And we will get S is equals to A over 1 minus R. That's to say, this term right here will approach 0 if absolute R is less than 1. Right? So here we have got the following formula here for geometric series. AR to the N equal to 0 to infinity, is equal to A over 1 minus R. This is a particular case of this. Here R is equals to half, and we're looking at summation R to the N going from 0 to infinity, where R is a half. 1 plus a half plus a quarter. The first term here, A, is a half. The ratio, R, is also a half. So this sum is going to be a half over 1 minus a half. 1 minus a half is a half. Whoops. The first term here is 1. That's what's wrong. When n equals 0, the first term is 1. So we get 1 over 1 minus a half, or it's 2 for the sum, which is what we'd expected here. Right? Another example of a geometric series, let's say 8 over 3 times 3 to the minus n. N going from, let's say, 0 to infinity. When n equals 0, the first term here is 8. The ratio is a third, so we end up with 8 over 1 minus a third, or 8 over 2/3, or 8 times 3 halves, or 12. So if we take the sum 8 times 3 to the minus n from n equals 0 to infinity, we end up with 12 for the total. It's really not the total. It's the limit of the partial sums. Right? There really is not a way in which you can sum these things up, although in some instances it appears that you can obviously get very close. Okay, so series and their sums. Okay, more in series here. If the partial sum, let's say I equals 1 through n of AI is Sn, and the limit of the Sn is equal to S, right? Then S is said to be the sum of the series. And well, if this is finite, then summation AI is said to converge. All right, so a sequence is said to converge if its limit is finite, and now we also say that the series converges. If Sn approaches infinity or minus infinity, then summation AI, you sometimes leave off the I equals 1 to infinity here, is said to diverge to plus infinity or minus infinity. If Sn does not have a limit, then summation AI is said to diverge, or you say that it diverges. So it's the definition of converge and diverge. I want to note something now that's an important property to look for, and that is this. If summation I equals 1 to infinity of AI is equal to S, finite S, then the limit as n approaches infinity of the AI is equal to 0. That's to say, the only way in which a series can converge is if the sequence, the corresponding sequence, approaches 0. Now, the converse is not true. If the sequence approaches 0, it doesn't mean that the series converges. But let's see why this is the case. Right? If it were not the case, if an did not approach 0, there would be an epsilon greater than 0 and infinitely many AI with their absolute values larger than that epsilon. Now what happens here is this. You look at this from the standpoint of a picture. If AI sums to S, or if summation AI were equal to S, then what would happen here? For any epsilon, in particular for this epsilon, we would have to have all the partial sums between S minus epsilon and S plus epsilon. If this was S, the limit. Right? In fact, what we would have to have them between S minus half of epsilon and S plus half of epsilon. But what happens here is that as soon as you get a term from the partial sum that's between S minus half of epsilon and S plus half epsilon, and you run across one whose absolute value is larger than epsilon, the next term is outside of this interval. When you add epsilon here, you're outside of this interval. And so consequently, if the limit of the AIs was not 0, then it would not be possible for the sum of the AIs to converge to any particular number S. As soon as they got close, they would have to, the sums would have to be away from that number S. Okay, but the converse isn't the case. Can be seen as follows. 1 plus a half plus a third plus a quarter and so forth here. That's to say the summation 1 over I equals 1 to infinity, diverges. That's to say this is equal to infinity. You can see that as follows. Let's follow this down a bit here. Let's look at a quarter plus a fifth plus up through a seventh, and then let's add an eighth, and so forth here, up through a 15th, and a 16th, up through a 31st, and let's look at these first terms of the series. Well, this term right here is larger than a half. This term is a half. These terms right here, a third plus a quarter, add up to something more than a half. Right? A fifth, a sixth, a seventh, and an eighth. So a fifth plus a sixth plus our 4 terms, all larger than an eighth. So those 4 terms add up to larger than a half. A ninth, all the way up through a 16th, are 8 terms, all of which are larger than a 16th, so they add up to more than a half. A 17th here, up to a 32nd, right? Those are 16 terms which are larger than a 32nd, they add up to more than a half. So this series has got to add up to as large a number as you would like here, the partial sums do, and so consequently the sum of the numbers 1 over I from 1 to infinity is infinite. Right? This particular series here is called the harmonic series. The harmonic series. Summation 1 over I. Okay, so convergence and divergence. If you've got convergence, then AIs must approach 0, and the harmonic series diverges. Now we're going to look at 5 tests for convergence to determine whether you've got the convergence or divergence of a series, and we'll be interested in series of positive terms, or non-negative terms at least. And the first of these is called the integral test. And it goes like this. If an is greater than or equal to 0, and if an is equal to f of n, where f is decreasing or non-increasing, then, so if this is the case, then summation an is less than infinity if and only if, like that is IFF, the integral from 1 to infinity f of x with respect to x is less than infinity. So we use the improper integral of f to determine whether or not this sum is finite. The picture for that looks like this. There really are 2 pictures. If we look at the sequence of natural numbers on the line here, 1, 2, 3, and so forth, and by hypothesis here, we've got some function f of x, like so, with f of n is an. Right? So, if we look at the size of this box right here, it's 1 unit wide by A1 high. This one is 1 unit wide by H2 high, so its area is H2. Right? A3, and so forth here. So that the summation an from 2 to infinity is going to be less than or equals to the integral from 1 to infinity of f of x with respect to x. See, if you look at all these boxes from the second one on here, they're all underneath the integral from the area. Their total is less than the area from 1 to infinity of f of x with respect to x. And we need a second picture here to complete this. Again, like so, if this is f of x, and here's 1, 2, 3, 4, 5, and so forth here. Now, if we draw a box to the right here, between 1 and 2, then this area is going to be A1, and this one here is going to be H2, A3, and A4, and so forth. And what we have here then is that the integral from 1 to infinity of f of x with respect to x is less than or equal to the sum from 1 to infinity of the an. That's to say, the area under the graph of f is contained in all of these boxes here. Right? So this sum is going to be larger than or equal to this. And this gives us this conclusion. Namely, that if this integral is finite, then the sum is finite because it's smaller than the integral. If the integral is infinite, then the sum is infinite because this sum right here is larger than the integral. Here, the sum from the second term on is smaller than the integral, so when you add the first term on, it'll also be smaller than the integral plus whatever the first term happens to be here. Right. One frequently writes the remainder of the series Rn to be equal to S minus the sum from 1 through n of the AI, where S is the sum from 1 through infinity of the AI. And then, this is the remainder after the first n terms have been summed, and it's clear from this picture here that Rn for example here, if we can think of this as n, Rn is going to be less than or equal to the integral from n to infinity of f of x with respect to x. And here, if we think of 4 as n, for example here, it's going to be greater than or equals to 4 is n here, it's going to be greater than or equal to the integral from n minus 1 to infinity of f of x with respect to x. Right? Rn, the terms from the, well here, let's check this for a second here. Rn, if n is 4, are the terms from the fifth one on out, and so this is going to be equal, less than or equal to the integral from n plus 1 to infinity, and this is going to be greater than or equal to the integral from n to infinity. Right? The sum of the terms from the fourth one out are going to be greater than or equal to the integral from 4 to infinity of f, and less than or equal to the integral from 5 to infinity, and in general, like so. Right? Let's look at a specific example here. Let's let an be 1 over n squared. So we let f of x be equal to 1 over x squared. And we find that the integral from 1 to infinity of 1 over x squared with respect to x. Well, an antiderivative here is going to be x to the minus 1 over minus 1. So we want to evaluate this from 1 to infinity. That's to say we want to take the value at t and subtract the value at 1, take the limit as t approaches infinity. Right? And this is going to be equals to, this t approaches infinity, this quantity goes to 0. And at the value of the function at 1, the value of this at 1 is minus 1. So 0 minus a minus 1, or 1. Now, what this says then is that this integral is equal to 1. All right? Suppose we look at the sum of the first 100 terms here. N equals 1 to 100, right, of the an, and we take 1 minus this. This is going to be our 100. It's the remainder to go after the first 100 terms have been added up. Right? And from this here, we get that this is less than or equal to the integral from 101 to infinity of f of x with respect to x, which is equal to x to the minus 1 over minus 1 evaluated from 101 to infinity, which is going to be 0 minus what? We've got minus 1 over 101. So 1/100th, or 101st for that matter, is how close you are when the first 100 of these terms have been added up. The next terms do not add up to more than 101st. Okay, so here's then the integral test. The remainder and an approximation for it, and an example of a series which does converge. 1 over n squared does converge now by the integral test. This integral is less than infinity, and the remainder is given by the bottom line here. Let's take a look at some examples where the integral test is used to show convergence. First of all, let's start with summation 1 over n to the pth power, n equals 1 to infinity, where p is larger than 1. Then, if we let f of x be 1 over x to the p power, f is decreasing, and to determine whether this converges or not, we want to take a look at the integral from 1 to infinity, 1 over x to the p with respect to x. And this is going to be equal to, what do we want here? X to the minus p, so we have x to the minus p plus 1 over minus p plus 1 is an antiderivative. We want to evaluate that from 1 to t here and take the limit as t approaches infinity. It's going to be equal to that. Right? And this is equal to the limit as t approaches infinity. We get the value at t to the minus p plus 1 over minus p plus 1, minus the value at 1, which is 1 over 1 minus p. Huh? Now, as t approaches infinity, since p is larger than 1, this is t to a negative power here, and so that this is less than infinity. It's equal to 1 over 1 minus p, 1 over p minus 1, right? Which is less than infinity. So this shows that this converges. This particular series converges by the integral test. We've already looked at this already. Let's look at summation 1 over n. We know that this diverges. Let's take a look at the integral test for it. Let f of x be 1 over x. And look at the integral from 1 to infinity, 1 over x with respect to x. And the antiderivative for 1 over x is log x, so we want to evaluate that from 1 to infinity. Let's say we take the value at t and let t approach infinity. Well, this is equal to what? The limit as t approaches infinity of log of t minus log of 1, which is infinity. So the integral is infinity of this function, and so the series sum 1 over n diverges. If we take a look at 1 over n to the p power with p less than 1. Right? We let f of x be 1 over x to the p. And look at the integral from 1 to infinity of 1 over x to the p dx. This is going to be, as before, x to the minus p plus 1 over minus p plus 1, evaluated from 1 to infinity. That's to say, it's going to be equal to the limit as t approaches infinity, t to the minus p plus 1 over minus p plus 1 minus 1 over minus p plus 1. But now, if p is less than 1, t to the minus p plus 1 is t to a power larger than 0, and as t approaches infinity, this is going to approach infinity. So infinity is this right here, and so we get that this diverges. This diverges, and this one here converges. Let's look at one more. Summation 1 over n log of n. And let's start here with, so we don't have a 0 in the denominator, let's start here with 2. Look at the sum n equals 2 to infinity. In which case, we want to let f of x be equal to 1 over x log x, and consider the integral from 2 to infinity of 1 over x log x dx. Right. Well, an antiderivative here, if we let u equal log x du is 1 over x dx, and for the antiderivative we're looking then at 1 over u du. So an antiderivative is logarithm of u. U is log x, so this is log x, evaluated from 2 to infinity. That's, well, log t approaches infinity as t approaches infinity, so this is equal to infinity. And so we get that this diverges by the integral test. So several examples for the integral test. These are ones that are worth noting. 1 over n to the p, for p greater than 1 converges. 1 over n to the p for p less than 1 or for p equal to 1. That's 1 over n to the p here diverges. 1 over n log n diverges. But we want to take a look at a second test for convergence. It's called the comparison test, and it's essentially still for series whose terms are non-negative. So if we're given an and bn, sometimes the set brackets are used around these, like so, to indicate a sequence. And sometimes one even writes n equals 1 to infinity, like this on the outside, indicate a sequence going from 1 to infinity. If there is an n, so that for all n bigger than that n, 0 is less than or equal to an is less than or equal to bn, then what happens is this. If summation an converges, if summation bn converges, then summation an converges. And secondly, if the summation an diverges, then the summation of the bn diverges. In fact, what? To infinity, right? All right. Let's see why. First of all, if we look at, if we've got this given, this number n, right? And we look at sk equal to the sum from k equals, I equals n plus 1, start right after n, and add this up to k, Then this quantity right here, Sk, the sum of the AI's, is going to be less than the sum from n plus 1 to infinity of the BI's, or equal to it. And Sk, see, if the sum from 1 to infinity of the BN's converges, then this converges too. In fact, it converges to the entire sum minus the sum of the first n terms. Now what happens here with this Sk? Sk are increasing. And bounded above. So they must converge. Right? If Sk approaches S, right, they're bounded above by this quantity right here, which is less than infinity. Because supposedly the sum of the BN's converges. If Sk approaches S, then the sum of the AI, I equals 1 to infinity here, is equal to the sum of the AI, I equals 1 through n, capital N, plus S. Because we've deleted the first n terms here, and now we add them back on again and add S to that, and the sum of the AI must converge. Sum of the AI converges. Conversely here, if the sum of the AN diverges, and this happens here, then summation AN is diverges to infinity here, because all these terms are positive from the nth one on, so they have to, if they're going to diverge, they have to add up to infinity. If they didn't, they'd be bounded above, and consequently would converge. Summation AN is infinity, and so consequently, what's going to happen here also is the summation BN is going to have to be infinity here, rather, because if the BNs, the sum from n to infinity of the BNs on would bound the sum of the ANs. So if this diverges to infinity, then this must diverge also to infinity here. Right? If the sum of the ANs diverges, it has to diverge to infinity because there's all positive terms from the nth one on. And then the sum of the BNs is going to be larger than its if we start from the nth one on and add them up. So it's going to have to diverge to infinity also. Two common series here that are used for comparison. One is the geometric series, summation, let's say p to the n, or a constant times p to the n, with absolute p less than 1, converges. Right? And so this is frequently used to compare to with other series. Another one that's frequently used is 1 over n to the p. Right? This converges if p is larger than 1. And so it's frequently used as the larger of the two in the comparison. This also diverges if p is less than or equal to 1. So for p less than or equal to 1, or for p equal to 1, it's frequently used as the smaller of the two to show divergence. So the comparison test and two frequently used types of series for the comparison test. We'll look at some examples next. Okay, we're going to take a look at some examples of the comparison test here. And the comparisons that are generally made here are as follows. Summation p to the n with absolute p less than 1 converges summation n to the p, both cases here n equals 1 to infinity, with p greater than 1 converges with p less than or equal to 1 diverges. So these are most commonly used comparisons here. Let's look at the summation 1 over n squared plus n. This converges because 1 over n squared plus n is less than 1 over n squared. And summation 1 over n squared converges. Huh? Let's take a look at summation 2 to the n plus 3 to the n over 4 to the n plus 5 to the n. This is going to converge. Because each of these terms here, in the numerator here, I would get something smaller. Let's look at it. 2 to the n plus 3 to the n over 4 to the n plus 5 to the n. I would get something larger if I replaced the 2 to the n with 3 to the n. So this is going to be less than 2 times 3 to the n in the numerator is. And in the denominator, I would get something smaller if I replaced the 5 with a 4. That's to say the whole thing would get to be larger. So this is less than 2 times 3 to the n over 2 times 4 to the n, which is 3/4 to the n, which is p to the n for p equal to 3/4, and so we get convergence. Summation log n over n diverges. Log n over n, after all, is larger than 1 over n, and 1 over n diverges. So this is going to diverges, in fact, to infinity here. Huh? But summation 1 over n times n plus 1 times n plus 2. This is going to converge because 1 over n times n plus 1 times n plus 2 is less than 1 over n cubed. 1 over n cubed converges. How about 1 over the square root of 2n minus 1? The summation. N equals 1 to infinity, say here. This is going to diverge. What we want to do is we want to compare that to 1 over square root of n. All right. Well, is it larger than 1 over square root of n? Not necessarily, but it's larger than 1 over 2 times the square root of n. Or it's larger than 1 over 3 times the square root of n, even better. And so 1 over square root of 2n minus 1, right, is larger than 1 over 3 square root of n. 1 over square root of n diverges up. So this must diverge. How about summation 1 over n factorial? Okay, this is going to converge. In fact, we know if this is from n equals 0 to infinity, this converges to e, yeah? That's, by the comparison test, though, 1 over n factorial is less than 1 over 2 to the n here, I guess. Maybe 2 to the n minus 1. So that 1 over 1 factorial is less than 1. 1 over 2 factorial is less than a half. 1 over 3 factorial is going to be less than a half squared. And it's clear that 1 over n factorial is going to be less than 1 over 2 to the n minus 1. This is geometric series here. That's 1 over 2 to the n minus 1. That's p equals 2. This is equal to a half times 1 over 2 to the n, or a half to the nth power. So half to the n power converges, so the constantly 1 over n factorial, we see immediately converges from this. We're going to look now at a second comparison test. This is sometimes called the limit comparison test. It's for series with non-negative terms, or at least non-negative terms from some point on. If a n is greater than or equal to 0, and b n is greater than or equal to 0, and the limit as n approaches infinity of a n over b n is equal to L, then 1, if summation a n converges and 0 is less than or equal to, is less than L is less than or equal to infinity, then summation Bn converges. So if the summation of the an converges, and this limit here is a number L, larger than 0, or possibly even plus infinity, then the sum of the Bn converges. Secondly, if summation an diverges, and 0 is less than or equal to L is less than infinity, then summation Bn diverges. It has to diverge to infinity too, because these are non-negative terms. All right, why? Well, if, first of all, 1 here, if summation an converges, and this limit is L, then if L is less than infinity, Bn is less than an well, here. Bn is less than, for large enough n, Bn is less than an well, L times Bn is less than an times 1 plus epsilon here, for epsilon. And so consequently, what? Summation an converges, so summation an times 1 plus epsilon does, so summation Bn does. And if L is equal to infinity here, and summation an over Bn approaches L, then what? Bn is going to be less than an period, and consequently summation Bn by the comparison test will converge. This is for n, for large enough n. Secondly, suppose that the summation an diverges. and an over bn approaches L, then bn, right, is going to be larger than an times 1 minus epsilon times L for large enough n. Right? Summation an diverges, summation an times 1 minus epsilon is going to diverge, and so summation bn is going to diverge. This is for L greater than 0. Right? Do this correctly here. I'm sorry. An over bn approaches L, so that L times bn is going to be larger than an times 1 minus epsilon for n large enough. And so consequently, what? Summation an is infinity, so summation lbn is infinity, and consequently summation bn is infinity, bn diverges. For L equal to 0, right, if an over bn approaches 0, and summation an diverges, then bn will have to be larger than an, huh, in order for this to approach 0 for large enough n. And now by the comparison test, bn is larger than an, so that summation bn diverges. Summation bn is infinity, it diverges. So this limit comparison test. Take a look at some examples. You want to take a look now at some examples of limit comparison test. Let's look at summation 1 over n plus log n. That's I'm going to use 1 over n here for the comparison function, so this, we're going to claim that this diverges with comparison to 1 over n. So what do? We've got an is 1 over n plus log n. I guess this is our bn that we want here if we're doing this. And we'll an be 1 over n. And now we look at the limit as n approaches infinity of an over bn. Right? And this limit is going to be the limit as n approaches infinity, n plus log n over n, right? Or the limit as n approaches infinity of 1 plus log n over n, and now recall that log n over n goes to 0, so that this is equal to 1. So that since the summation an diverges, the summation bn diverges. Let's look at the summation log of n over n to the p. For p larger than 1. Right. And let's choose here for the comparison 1 over n to the q, where p is larger than q larger than 1. So p is supposed to be larger than 1 here. We choose some q which is between p and 1, and we use this for the comparison. So this is going to be equal to bn, and an is going to be equal to 1 over n to the q. We want to take a look at the limit, if it exists, as n approaches infinity, of 1 over n to the q divided by log n over n to the p. Right? And now what? This is equals to the limit as n approaches infinity. We've got 1 over n to the q minus p times log n. Right? Since q is less than p, q minus p is negative, so this, if you like, is equal to the limit of n to the p minus q over log n as n approaches infinity. Right? And now n to the p minus q goes to infinity faster than log n. So that consequently this limit is infinity. You can check that using L'Hopital's rule if you wish. Right? So what does that mean? It says that, okay, this limit right here, this was an, this was bn down here. The limit of an over bn gets to be very large. Right? So bn is basically a lot smaller than an eventually. Right? An converges, so bn must converge. Right? You can get the sense of this limit comparison test here by just thinking it through a little bit. So this converges. Okay, so here are two examples then of limit comparison test. One where the sum diverges, and the other one where it converges. But before we continue with the test for convergence, we want to look at several different types of series. First of these is called an alternating series. An example of this is 1 minus a half plus a third minus a quarter plus a fifth minus a sixth and so forth. The idea being that the terms alternate, their sign alternates. So an alternating series is a series of the form summation minus 1 to the n an, where each an is greater than or equal to 0. Or it could start with the negative terms here, or positive, minus 1 to the n plus 1 times an, where each an is greater than or equal to 0. And we also want here is, we want to insist on here, for an alternating series, is that an approaches 0. Particularly, what we want is that an decreases with an approaching 0. And in that case, if this is by what we mean, this is what we mean by an alternating series, here's an example of one, then alternating series always converge. You can see that pictorially very easily. Let's suppose, for simplicity here, that the first term is positive, and so here's a1. And now to get a1 is of course equal to the first sum, the sum of the first one term here. a1 plus h2 well, A1 minus H2, if you want here, if it's written this way, is S2. So if we go up here to A1, we want to go back in this direction here. Went up to A1, go back in this direction. Here's S2. It's A1 minus H2. S3 is A1 minus H2 plus A3. And A3 is smaller than H2, so we went back this direction, quantity of H2. We now go back this direction here like so. So we're here at S3, which is less than A1. And then S4 is back this direction here like so. Right? And we end up with here is a sequence of intervals. We end up with this interval right here, like so, and then this interval right here, and then this interval right here, like so, and then this interval like so, and from once the sum is in here, it's going to go back and forth in here. And the intersection of these intervals, since the AN goes to 0, is going to be a single point. A single point is the sum of the series. It's the limit of the partial sums. These partial sums have to go back and oscillate back and forth here in smaller and smaller intervals. In fact, the remainder term Rn, right, is less than absolute An plus 1. If we're writing this like this, it's less than An plus 1, or equal to it. The error term can be no larger than An plus 1. So that, for example, here if we took a look at 1 minus a half plus a third minus a fourth, and so forth here, so we get out to plus a 99th and minus 100th, right? This is going to be the sum from 1 through 100 of 1 over n times minus 1 to the n, and Rn here is going to be, the remainder that's needed here is going to be less than 1 over 101. That's to say, we're within 101st of the total sum here at this point. And this sum converges, although, of course, the harmonic series, 1 plus a half plus a third plus a fourth and so forth, does not converge. So this converges. It's an example of an alternating series whose terms go to 0, decrease to 0, always converge. And you can see it pictorially that they have to converge to this point, which is, the point is really what? It's the least upper bound of the even terms of the Sn, or it's the greatest lower bound of the odd ones. Before we finish with the tests for convergence, we want to look at what's called absolute convergence. If we've got a sequence AN, then summation AN is said to converge absolutely if summation absolute AN is less than infinity. Now, if summation absolute AN is less than infinity, then summation AN converges. The converse doesn't have to happen, but if you've got absolute convergence, then you automatically have convergence. Right? So given a sequence here, the sum is said to converge absolutely if the sum of the absolute values is less than infinity. And the conclusion is going to be then that this converges. We'll see that in just a second. If summation AN converges, and summation absolute AN is infinity, then summation AN is said to converge conditionally. So use the word conditional convergence if there's convergence, but the convergence isn't absolute. All right. Let's see that absolute convergence implies convergence. So suppose summation absolute AN is finite. It's less than infinity. And let Bn equal to AN plus absolute AN. Then, what? Bn, each Bn is greater than 0, or equal to 0, and it's less than or equal to absolute AN. So, by the comparison test, summation Bn converges. It's positive, and it's less than 2 absolute AN, which converges. Right? But now AN is equal to AN here is equal to Bn minus absolute AN, so that summation AN is summation Bn minus summation absolute AN, and summation AM converges. Huh? It's easy to see for any sequences that if you've got two convergent sequences, then the difference of the two converges also, and it converges to this. Huh? So if AN converges absolutely, then it converges, period. Right? Okay. Take a look at some examples here. Let's look at sine of n over n squared. I'm going from 1 to infinity. Does this converge? Yes, it does, because it converges absolutely. This sine of n over n squared, well, actually, I guess we want absolute sine n here, over n squared. Now, sine n over n squared, that's okay. Sine n over n squared in absolute value, right? We want to show that this converges, and this is less than 1 over n squared. So by comparison, summation 1 over n squared is less than infinity, so summation sine n over n squared is less than infinity. And so consequently, sine n over n squared converges absolutely, so sine n over n squared converges. And you're going to have positive and negative terms depending upon where n is. Summation minus 1 over 2 to the n, O times log n. Or times 1 over log n. That's log n. Right. Well, instead of looking at this right here, we look at 1 over 2 to the n times log n. Right. And what? This is going to be less than log x, log n over 2 to the over e to the n. Well, half of e to the n. To make some sort of a comparison here. Actually, what we want to do here with this is to use an integral test on it and look at log x over 2 to the x, like so. Right. And we'll find that this converges absolutely. So consequently it converges. This converges in both cases here because of absolute convergence. That's to say, you don't worry about the sign of this thing here. We look at log n over 2 to the n. All right? And we want to see that it converges. And once we've seen that it converges, then the original one will converge. This is perhaps not the best choice here because it's going to take considerably more to show that it's going to converge. Now look at the fourth test here now for convergence called the ratio test. And it's really a test for absolute convergence. And it looks like this. Here's a sort of the least general form of it, or a form of it. If we've got an, all right, and we want to consider summation an, right, and we have that the limit of absolute an plus 1 over an is equal to r less than 1 as n approaches infinity, then summation an converges. If it's equal to s greater than 1, then summation an diverges. Right. Now, actually, if this limit is equal to s greater than 1, the divergence follows from the fact that the terms don't even go to 0. an plus 1 over an does not even go to 0. Right. This part of the test here, the limit be equal to r less than 1, actually could be slightly improved as follows. If there is an n, so that for n larger than n, an plus 1 over an, the absolute value here, is less than r, which is less than 1, then summation an converges. Actually, summation absolute an converges. Right? So we don't really have to have the limit be equal to r. We just have to have, for some n larger, there has to be some r and an n, so that for n larger than n, this is less than that number r. Because then what happens is this. Let's suppose that an plus 1 over an in absolute value is less than r. Right? We can write this like so. Then what this says here is that an plus 1 in absolute value is less than r absolute an. Now we also have here what? That an plus 2 over an plus 1 in absolute value is less than r. So what we get from that is that an plus 2 is less than r absolute an plus 1, which is less than r squared absolute an. And an plus 3 over an plus 2 in absolute value, this is going to be less than r. So an plus 3 in absolute value is going to be less than r times absolute an plus 2, which is going to be less than r squared times absolute, well, it's going to be less than r cubed here, absolute an. Right? In general here, a sub n plus k in absolute value is going to be less than r to the k absolute an by just continuing this process right here. N plus 1 is less than r, n plus 2 is less than r squared. The n plus k term, right, is going to be less than r times the n plus k, the n plus k minus 1, and that's going to be less than than r to the k. This constant is going to be less than r to the k times absolute an. Okay, but now what happens here is this. What happens is that if we look at the sum, a n plus k, from k going from 1 to infinity, this is less than an plus 1, this is an absolute value, times the sum of r to the k power. That's to say, we can now compare these terms here, an plus 1, an plus 2, an plus 3, and an plus k, with a geometric series. R times an, r squared times an, r cubed times an, r to the k times an. So this converges. So the sum from n plus k converges, and so consequently we have the sum absolute ai converges. And the ratio test then guarantees convergence, but not only convergence of the absolute value of the terms in the series, the sum of the absolute values. Let's take a look at some examples of the ratio test. Let's take a look at, for example, summation over 2 to the n. We want to look at the limit, if there is one, of the an plus 1th term over the anth term, an plus first, as n approaches infinity. All right. This is going to be equals to n plus 1 over 2 to the n plus 1 divided by n over 2 to the n. Okay, which is going to be equals to n plus 1 over n times half, which approaches a half. And so this the ratio test says this converges. Right. So the comparison test, for example, says something like log n over 2 to the n converges, which answers the question of a different nature here from before. Log n over 2 to the n converges absolutely. Right. How about n squared over 2 to the n? Well, we want to look at the limit as n approaches infinity of n plus 1 squared over 2 to the n plus 1 divided by n squared over 2 to the n. This is going to be n plus 1 squared over n squared, again times a half, and the limit is going to be, as n approaches infinity of this, is going to be equals to a half. And so you get convergence here again. It's even clear here that at the end of the k over 2 to the n, you're going to get convergence. Because by the ratio test here, you're going to get a half times n plus 1 to the k over n to the k, and the limit's going to be a half. Right. Let's look at something perhaps a little more tricky here. N factorial squared, how about that over 2n factorial? Does that add? Right. Well, we want to check it with the ratio test. And we're going to get what? N plus 1 factorial squared over 2 times n plus 1, or 2n plus 2 factorial. That's the n plus first term. And this divided by n factorial over 2n factorial. Okay? And now if we invert this here, we get that this is equals to n plus 1 factorial times n plus 1 factorial over n factorial times n factorial. And now we've got, in the denominator here we've got 2n plus 2 factorial. And the numerator here we've got 2n factorial. So this is going to be equal to what, n plus 1 times n plus 1, and then the 2n into 2n plus 2 factorial is going to leave us with 2n plus 2 times 2n plus 1. This approaches a quarter as n approaches infinity. We've got a polynomial in n of degree 2 here in numerator and denominator. The leading coefficient here is 1, and this is 4. So this approaches a quarter, and so the ratio test says that this converges. Right. Let's note the following, though, huh? This makes this ratio test look like as if it's pretty powerful, and it is when it works. Right? But let's consider 1 over n squared, which we know converges. All right? The ratio test says we should look at 1 over n plus 1 squared divided by 1 over n squared. And this is equal to n squared over n plus 1 squared, which approaches 1. And so the ratio test doesn't tell you. You can't tell by the ratio test whether this converges or not. Well, clearly converges, and we got it originally here using the integral test. So this converges, but you can't tell it using the ratio test. Here are some examples where the ratio test tells you that you've got convergence. Let's take a look at some additional examples involving the ratio test. Let's suppose we look at summation 10 to the n over n factorial. Right? We should be looking then at the limits as n approaches infinity. Absolute an plus 1 over absolute an, which is going to be, in this case here, 10 to the n plus 1 over n plus 1 factorial divided by 10 to the n over n factorial. Okay, this is going to be equals to 10 over n plus 1, which goes to 0, so that the ratio test says this converges. We get 10 to the n, and 10 to the n plus 1 gives the 10. We get n factorial over n plus 1 factorial gives the n plus 1. All right. How about summation n factorial over n to the n? Well, we want to take a look at n plus 1 factorial over n plus 1 to the n plus 1 divided by n factorial over n to the n. This is going to be equal to, what do we have here? N factorial into n plus 1 factorial is going to be n plus 1. We're going to have n plus 1 to the n plus 1 in the denominator here, and n to the n in the numerator here. Okay, we want to know what happens to this. What? We could cancel the n plus 1 and the n plus 1 to the n plus 1, and we get that this is equal to n to the n over n plus 1 to the n, which is equal to n over n plus 1 to the nth power. Now, what is the limit? We need the limit as n approaches infinity of this. Let's change this to x's. As x approaches infinity of x over x plus 1 to the xth power. this looks like the time to use L'Hopital's rule. Right? After we've rewritten this, that's to say this is